and get you up to speed fast. Today, we're tackling one of the biggest questions out there. But does that picture, that sort of cinematic idea, actually match up with the science?
It's a really powerful image, isn't it? Super common. But yeah, as we'll see from the sources you've gathered, that whole explosion idea is, well, fundamentally misleading. So our mission today is to unpack what the science really says about the universe's beginning, look at this fascinating stuff called antimatter, and then reveal this deep cosmic puzzle that's still keeping physicists busy.
Exactly. So, yeah, prepare for some, hopefully, aha moments. We'll break down the term Big Bang itself. We'll look at the main scientific model we use, get a handle on antimatter, which is pretty wild stuff. And then, crucially, see how the fact that we even exist points to this tiny, tiny imbalance way back at the start. Okay, let's kick off with the Big Bang. That phrase itself, it just screams explosion. Is that what scientists actually mean?
Not really, no. It's funny, the history of the term is actually quite revealing. The sources point out it was coined by astronomer Fred Hoyle, kind of dismissively. He didn't actually believe in the theory. He favored something called the steady state model. So he used Big Bang almost to, well, make fun of it.
Seriously. So it was like a nickname meant to mock the idea.
Yeah.
And it just stuck. And that's why we all think of a giant bomb going off in space.
Precisely. But the standard scientific picture, the Lambda-Cold Dark Matter model, or CDM for short, it describes something completely different. ACDM basically weaves in dark energy, that's the lambda part, and cold dark matter. It's not describing an explosion in space, it's talking about the expansion of space-time itself. Starting from this incredibly dense, incredibly hot state about, 13.8 billion years ago?
That's a huge difference. So space and time aren't just the stage, they're part of the action dynamic. So the where of the Big Bang isn't some specific spot, it's everywhere at once. And asking what came before might not even make sense because time itself kind of started that.
That's the idea, yeah. Grasping that distinction, expansion of space versus explosion in space, that's really the first crucial step.
All right, let's dig into the CDM model then. Our universe's blueprint. What's it built on? What makes scientists so confident in it?
Well, it stands on two really big ideas. First, Einstein's theory of general relativity. It assumes that correctly describes gravity on the grandest scales, cosmic scales. And second, something called the cosmological principle. This basically says that if you zoom out far enough, the universe looks pretty much the same everywhere that's homogeneous and in every direction that's isotropic. So no special center, no edge, which makes the math a lot simpler, thankfully.
Okay, but are those just convenient assumptions? Or is there actual proof they're true?
Oh, there's really strong observational backing. Things like the cosmic microwave background radiation, the CMB, it's incredibly uniform. And how galaxies are spread out across vast distances, it all lines up extremely well with that cosmological principle.
So if we run the clock backwards using this model, we get to this super hot, super dense beginning. What was happening right at the very, very start?
Well, right at the absolute beginning, like the first tiny fraction of a second, what we call the Planck time, around 1043 seconds, our current physics kind of breaks down. We'd need a theory of quantum gravity, which we don't have yet. But shortly after that, between about 1036 and 1032 seconds, something truly remarkable is thought to have happened. Cosmic inflation.
Inflation. That sounds like it implies a ridiculously fast expansion. Like way faster than normal.
Oh, unbelievably fast. Exponential expansion. Space-time just blew up, stretching by a factor of at least 1026, maybe much more. This smoothed everything out, erasing irregularities. And this is key. It blew up tiny quantum fluctuations, like little jitters in space-time, to enormous sizes. Those became the seeds for galaxies, clusters, everything we see. Then, at the end of inflation, all that energy dumped into creating a hot soup of particles and radiation. That set the stage for the slower expansion we see today.
Wow, that's mind-bending. And this whole CDM picture isn't just theory, right? You mentioned evidence, the 4 pillars, I think the sources called them.
That's right. 4 key lines of evidence. Pillar 1, the expansion of the universe. We know this thanks to Edwin Hubble back in the 1920s. He saw distant galaxies are moving away from us, and the farther away they are, the faster they go. That's Hubble's law. The light gets stretched, redshifted, we call it. If you trace that expansion back, everything must have been closer together, hotter, denser in the past.
Okay, expansion. Pillar 2 is the CMB, the cosmic microwave background. You said it's super uniform. How is that a pillar?
Right, the CMB. It was predicted by the model before it was found, which is always a good sign. Discovered kind of by accident in 1964, it's this faint microwave glow coming from everywhere. It's basically the leftover heat from the Big Bang, a snapshot of the universe when it was only about 380,000 years old. Back then, it cooled to about 3,000 Kelvin, Cool enough for electrons and protons to finally hook up and form neutral hydrogen atoms. That's called recombination. Before that, light couldn't travel far. The universe was like a dense fog. After recombination, it became transparent. Those photons have been traveling ever since, cooling down to just 2.73 Kelvin today. Its near-perfect smoothness confirms the cosmological principle. But crucially, it has tiny temperature ripples, tiny fluctuations. Those match the seeds of structure predicted by inflation.
A baby picture of the universe showing both smoothness and the initial lumps that grew into galaxies. Amazing. What's pillar number 3?
Pillar 3 is Big Bang nucleosynthesis, or BBN. This happened in the first few minutes. The universe was so hot and dense, it was basically a nuclear furnace. Conditions were just right to fuse protons and neutrons into the lightest elements. The model predicts precisely how much should have formed. About 75% hydrogen, 25% helium-4, plus tiny traces of deuterium, heavy hydrogen, helium-3, and lithium. And when we look at the oldest, most pristine gas clouds in the universe, that's exactly the mix we find. It's incredibly strong evidence for that hot, dense early phase.
So the ingredients were cooked right at the start.
Got it.
And the final pillar.
Pillar 4, the formation of large-scale structure. How did we get from those tiny ripples in the CMB to the vast cosmic web of galaxies and voids we see today? Well, gravity acted on those initial density variations. The slightly denser spots pulled in more matter over billions of years, and the less dense regions emptied out. This gravitational snowballing formed stars, then galaxies, then clusters of galaxies. The patterns we see in galaxy surveys, how they cluster, match the predictions based on those CMB ripples perfectly.
Okay, so expansion, the CMB, the light elements, the structure, they all fit together within this CDM framework. It seems incredibly successful. But you said earlier, it doesn't explain everything.
No, it doesn't. Big mysteries remain. Like, what is dark matter? What's driving the accelerated expansion, this dark energy? And the big one for us today, why is the universe made almost entirely of matter with hardly any antimatter? That's the baryon asymmetry problem. CDM describes the stage, but not why the actors are mostly matter.
Right, the core mystery. Okay, so to get into that, we need to understand antimatter itself. Sounds like something from Star Trek, but it's real physics.
Oh, absolutely. It came right out of fundamental theory. Paul Dirac, back in 1928, was combining quantum mechanics and special relativity. His equation predicted a particle just like the electron, but with opposite charge, an anti-electron. And just a few years later, 1932, Carl Anderson found it in cosmic rays. He called it the positron. That discovery confirmed, for every particle, there's an antiparticle.
So antimatter is like matter's mirror image.
Pretty much. Same mass, same spin, but opposite charge. And other quantum numbers, like baryon number for protons and neutrons or lepton number for electrons and neutrinos, are also flipped. So an antiproton has negative charge. An antineutron is neutral, like a neutron, but its internal quark structure and magnetic properties are reversed.
Could you build things out of it? Like anti-atoms, anti-stars?
In principle, yes. And experimentally, scientists at CERN have actually made antihydrogen, an antiproton orbited by a positron, and trapped it. They've even checked how it behaves in gravity. And guess what? It falls down, just like regular matter, not up. That was a big question to answer.
Okay, so we have matter and its opposite, antimatter. What happens if they actually meet?
That's where Einstein's IMSI part really shines. Two key things happen. One is pair production. If you have enough energy concentrated, say a really high energy gamma ray photon passing near an atom's nucleus, that energy can convert directly into mass. But, and this is critical according to the sources, it always creates a particle and its antiparticle partner. An electron and a positron, for example, always in pairs, equal amounts.
Always equal amounts from energy. Okay, and the opposite?
That's annihilation. Particle meets antiparticle. Poof. They destroy each other completely. Their entire mass is converted back into pure energy, usually high-energy photons, gamma rays. It's the ultimate energy release. Just a tiny amount, like a gram of matter and a gram of antimatter annihilating, would release energy like a nuclear bomb. For protons and antiprotons, it can produce a whole spray of other particles, too.
Okay, this symmetry created in pairs, annihilate, completely seems fundamental.
Right.
But if you apply that to the very early universe, that leads to a huge problem for us, doesn't it?
A profound problem, yes. Particle physics experiments confirm this symmetry holds incredibly well. So the Big Bang, starting from pure energy, should have created exactly equal amounts of matter and antimatter. Then, as the universe cooled, they should have found each other and annihilated, almost perfectly. What should be left? Basically, a universe filled with photons, maybe some neutrinos, but almost no matter. No protons, no neutrons, no atoms.
But here we are. We're made of matter. The Earth, the Sun, galaxies. It's all matter. We don't see huge clouds of antimatter floating around.
Exactly. Our existence is the smoking gun proof that something broke that perfect symmetry. Somehow, in those first fiery moments, a tiny bit more matter must have been produced or survived compared to antimatter. That tiny leftover fraction is everything we see. And that is the baryon asymmetry problem. It connects the biggest cosmology questions to the smallest particle physics details.
So let's be clear. The popular idea of a matter-antimatter explosion causing the Big Bang isn't right. The real puzzle is why the universe wasn't just instantly annihilated back into energy right after the Big Bang started.
That's the heart of it. It's arguably one of the biggest motivations for looking for physics beyond our current standard model. And the imbalance needed is incredibly small. The best estimate, fitting observations like the CMB, is that for every, say, 1 billion pairs of particles and antiparticles created, there was just one extra particle of matter.
One extra particle for every billion pairs. That's it.
That's it. The billion pairs annihilated, producing the huge bath of photons we see as the CMB today. That lone survivor, that 1 in a billion leftover, is what built everything else. All the stars, all the galaxies, you, me. We are the tiny asymmetry. It's why, as they say, there's something rather than nothing. We can even measure this ratio, the baryon to photon ratio, and it confirms this picture.
Mind blown. 1 in a billion. Okay, so how could such a specific imbalance possibly arise? What needed to happen?
Well, back in 1967, the physicist Andrei Sakharov figured out the essential requirements. 3 conditions, now called the Sakharov conditions, that absolutely must be met for any physical process to generate more matter than antimatter from an initially symmetric state. These aren't just suggestions. They're like the fundamental rules of the game if you want to end up with a matter-dominated universe.
Okay, condition number 1.
First, you need baryon number violation. Baryon number is basically a count of matter particles minus antimatter particles, like protons count as +1, antiprotons as -1. In all our lab experiments, this number seems to be conserved. You don't just create protons out of nothing. But if the universe started perfectly symmetric, net baryon number 0, and ended up with a positive baryon number, mostly matter, then some process must have existed that could change this number. It's thought this can happen at extremely high energies.
So, rule 1. The fundamental laws had to allow for creating matter without an equal amount of antimatter under some extreme conditions. Okay, second condition.
Second, you need C and CP symmetry violation. C symmetry is charge conjugation swapping particles with antiparticles. CP adds parity inversion looking in a mirror. If the laws of physics were perfectly C and CP symmetric, then any reaction that creates a matter particle would happen at exactly the same rate as mirror reaction creating an antimatter particle. Net result, 0 asymmetry. So the laws themselves must have a slight bias, a slight preference for matter over antimatter reactions. We have observed CP violation in particle experiments, specifically with quarks, but the amount we see in the standard model is way too small to explain the cosmic imbalance.
We see the bias, but it's not strong enough. Interesting. And the third Sakharov condition.
Third, you need departure from thermal equilibrium. If these baryon number violating, CP violating interactions happened while the universe was in perfect thermal equilibrium, nice and stable, then any reaction creating matter would be perfectly balanced by the reverse reaction destroying it. You wouldn't build up any lasting asymmetry. You need things to be happening too fast for equilibrium to keep up. The incredibly rapid expansion and cooling of the very early universe provides exactly this kind of out-of-equilibrium condition. Processes could happen, create an imbalance, and then the universe cooled so quickly the reverse processes couldn't erase it. It froze in.
Okay, baryon number violation, C and CP violation, and out-of-equilibrium conditions. Those are the ingredients. So what theories actually try to mix these ingredients together? How have the ideas evolved?
Well, the search for the specific mechanism called baryogenesis has gone through phases. One of the earliest ideas was GUT baryogenesis.
GUT's grand unified theories? Those try to merge the fundamental forces at super high energies, right? How do they explain the matter excess?
Exactly. GUTs naturally predict the existence of new, extremely heavy particles, sometimes called X and Y bosons. The idea was simple. In the ultra-hot early universe, these X bosons and their anti-X antiparticles were abundant. As the universe cooled, they decayed. If their decays violated baryon number and CP symmetry and happened out of equilibrium because the universe is expanding so fast, the X might decay slightly more often into matter particles, while the anti-X decayed slightly more often into, well, also matter, effectively, leading to a net matter surplus.
Seems plausible. Why isn't it the leading theory anymore?
Couple of big problems. First, many models of cosmic inflation suggest the universe might not have gotten hot enough after inflation to actually produce these super heavy X bosons in the first place. The reheating temperature might have been too low. Second, even if you made the asymmetry way back then, there's a process involving standard model particles called sphalerons that becomes active later around the electroweak phase transition. These sphalerons can effectively erase any pre-existing baryon asymmetry unless it has a specific property conserving B minus L baryon minus lepton number.
So the cosmic janitors might have cleaned it up later. Is there any way around that for GUTs?
There's a more recent twist, yeah. Some models propose that primordial black holes, if they formed early on, could evaporate later via Hawking radiation. If they evaporated after the electroweak transition when sphalerons were inactive, they could potentially produce those heavy GUT particles whose decays would then generate the asymmetry safe from erasure. It's an intriguing possibility.
Okay, so GETs have challenges, but maybe a lifeline. What came next?
The focus shifted to potentially lower energy scales, leading to electroweak baryogenesis, EWBG. The appeal here is that it ties baryogenesis to the electroweak scale, around 100 GeV or so. That's energy we can actually probe at the LHC.
How would that work? At the time, the electroweak force separated from the electromagnetic force.
The idea needed a specific kind of phase transition, a strong first-order one. Imagine the early universe cooling and bubbles of our current vacuum, where the Higgs field is on, start forming and expanding rapidly within the older symmetric phase. If there were new sources of CP violation beyond the standard model, interactions with these expanding bubble walls could treat particles and antiparticles differently. This could create an imbalance, which then gets converted into a baryon asymmetry by those same sphaleron processes, but this time they help create the asymmetry inside the bubbles where it's preserved.
But the sources say standard model EWBG is basically ruled out. Why?
Two main reasons. First, the measured mass of the Higgs boson, 125 GeV, tells us the electroweak transition was actually a smooth crossover, not that violent, bubbly first-order transition needed for the mechanism to work. Second, as we said, the amount of CP violation within the standard model itself is just far, far too weak. So for EWBG to work, you need new particles and new sources of CP violation beyond what we currently know, and we haven't found them yet.
Okay, so GTs are tricky. EWBG needs new physics we haven't seen. Where does that leave us? What's the front-runner theory now?
The current leading candidate, and arguably the most elegant, is leptogenesis. It flips the script slightly. Instead of creating the baryon asymmetry directly, it proposes that the universe first developed an asymmetry in the lepton sector, meaning an excess of leptons like neutrinos over their antiparticles, antineutrinos.
An excess of neutrinos first. How does that help with protons and neutrons?
Because those standard model sphaleron processes, the ones that were a problem for GUT baryogenesis, they naturally convert lepton asymmetry into baryon asymmetry. They shuffle things around but preserve the difference between baryon and lepton number, BL. So if you make a lepton excess first, the sphalerons automatically turn some of it into the baryon excess we observe.
Clever. So where does the initial lepton asymmetry come from?
The theory points to hypothetical, very heavy right-handed neutrinos. These are sometimes called sterile neutrinos because they don't interact via the known forces, except gravity and maybe the Higgs interaction. These heavy neutrinos are predicted by the seesaw mechanism, which is the most popular explanation for why the known neutrinos, electron, muon, tau, have such incredibly tiny masses. The idea is that these heavy neutrinos existed in the early universe. They decayed out of equilibrium, and if their decays violated CP symmetry, they could produce more leptons than antileptons. Voila, leptogenesis.
Wow, so it connects the matter-antimatter puzzle directly to the mystery of neutrino masses. That sounds neat.
It's very appealing, yeah. It explains two major pieces of evidence for physics beyond the standard model with one core idea. The main challenge is that these heavy neutrinos would be so massive we can't produce them directly in colliders to study them. But the theory does make predictions about the properties of the light neutrinos we can study. So this whole progression from GUTs to EWBG to leptogenesis really shows science refining ideas based on new data, like inflation models, LHC results, and the discovery of neutrino mass.
It's a fascinating scientific detective story. But is any of this actually being tested? Are experiments looking for clues right now?
Absolutely. This isn't just theorists dreaming. There's a huge experimental effort. For probing CP violation, we already mentioned the LHCb experiment at CERN. They have definitely observed CP violation in the decays of baryons containing heavy quarks, like the beauty lambda baryon. So we know CP violation happens with baryons, which is a necessary piece of the puzzle. But crucially, the amount they see is perfectly consistent with the standard model prediction. It's not enough extra CP violation to explain the universe's matter dominance. It tells us we need new sources.
Okay, so we've confirmed a necessary ingredient exists, but not in sufficient quantity in the known rules. What about looking for baryon number violation itself?
Yes, that's the goal of probing baryon number violation. Huge underground detectors like Super Kamiokande in Japan and the next generation experiments Hyper Kamiokande and DUD in the US are essentially giant vats of material waiting to see if a proton inside ever decays. Proton decay is a key prediction of many GUT models. So far, nothing has been seen. The experiments have set incredible limits. The proton lifetime must be longer than 44 years for certain decay modes. That already rules out the simplest GUT models. They also look for other exotic processes like neutrons spontaneously oscillating into antineutrons.
Waiting for a single proton to decay in potentially trillions of years. The patience involved. And for leptogenesis, what are the key experimental searches there?
For leptogenesis, the focus is on probing lepton number violation and neutrino properties. A major target is the search for neutrinoless double beta decay. This is a hypothetical, very rare type of nuclear decay that can only happen if neutrinos are their own antiparticles, what we call Majorana particles, and if lepton number isn't conserved. Finding it would be massive support for leptogenesis. Also, experiments like DUENE and Hyper-K are designed to measure neutrino oscillations with unprecedented precision. By comparing how neutrinos and antineutrinos oscillate, they hope to measure the CP violating phase in the neutrino sector. Is there CP violation among neutrinos? Leptogenesis models often predict there should be.
Incredible experiments, deep underground, giant colliders,
Yeah.
all trying to piece together why we're made of matter. But just to cover all bases, the sources mention alternative ideas, right? Where annihilation wasn't just a cleanup step, but maybe central to the universe's dynamics.
Right. While the standard model grapples with the asymmetry, there have been alternative frameworks built on the idea of perfect matter-antimatter symmetry. The most prominent is the Alphen-Klein model, or plasma cosmology, championed by Nobel laureate Hannes Alphen and Oscar Klein.
Plasma cosmology. That sounds very different. What's the core idea?
It's a radical departure. It assumes the universe is, on the whole, perfectly symmetric. Equal amounts of matter and antimatter exist, but they're separated into vast regions, or cells. Our observable bit of the universe just happens to be inside a matter cell. Somewhere out there, maybe incredibly far away, are antimatter galaxies and antimatter cells. It also gives electromagnetism and plasma physics a much bigger role in shaping cosmic structures than gravity, arguing that since most visible matter is plasma, those forces should dominate.
Okay, so we're just in a local matter bubble. What about cosmic expansion in this model? Is there still a Big Bang?
No Big Bang in the traditional sense. It rejects the idea of space-time itself expanding. Instead, it proposes that the Hubble expansion we observe is a more local effect, driven by ongoing annihilation happening at the boundaries between these matter and antimatter cells. That annihilation would release huge amounts of energy and radiation, pushing the cells apart, creating an outward pressure that looks like expansion from within a cell. Alphen argued this was the only known physics powerful enough for the job. It also implies an eternal universe, no beginning.
That's a completely different picture.
Ah.
But it sounds like it makes some testable predictions. Why isn't it the mainstream view? What observations contradict it?
It fails several crucial tests, which is why it's not the standard model. The biggest killer is the missing gamma ray background. If these matter-antimatter domains existed, their boundaries should be constantly annihilating. This would fill the universe with a diffuse glow of high-energy gamma rays. We've looked very carefully with gamma ray telescopes. It's just not there. The limits are incredibly strong, effectively ruling out this central idea.
No glow from annihilation boundaries. Okay, that's pretty definitive. What else?
The cosmic microwave background is another major hurdle. Plasma cosmology really struggles to explain the CMB's perfect blackbody spectrum, the precise distribution of its energy across different wavelengths. And its incredible smoothness across the sky is also hard to account for. Their explanations involving radio fog from plasma filaments just don't match the high-fidelity data we have from CMB telescopes like Planck.
And what about the light elements? BVN?
Yeah, Big Bang nucleosynthesis is another nail in the coffin. Without that initial hot, dense phase, plasma cosmology can't explain the observed abundances of light elements like deuterium and helium-4. It has to rely solely on stars to make elements. But stars destroy deuterium, they don't make it, and they don't produce nearly enough helium-4 to match what we see in old gas clouds. The observed deuterium abundance is considered really strong evidence for a Big Bang-like origin.
So it sounds like while the Alphen-Klein model had some interesting ideas, it made predictions that were directly contradicted by observations.
Exactly. That's how science progresses. It made clear, falsifiable predictions. And high-precision observations showed those predictions were wrong. ACDM, on the other hand, despite its own remaining puzzles like dark matter and dark energy, has successfully passed every major observational test thrown at it so far.
Okay, what a fascinating exploration. Let's
Yeah.
try to wrap this up and pull together the main threads.
I think the biggest takeaway is that the common image of a matter-antimatter explosion causing the Big Bang is just not right. It mixes up distinct concepts. The Big Bang, in our standard understanding, CBM, wasn't an explosion in space. It was the beginning of space and time itself, followed by rapid expansion from an incredibly hot, dense state. Those alternative annihilation-driven models just don't fit the evidence.
Right. But annihilation did play a huge role within the standard Big Bang story, just not as the initial cause.
Absolutely crucial role. That near total annihilation of the initial matter and antimatter pairs in the first second or so is what created the overwhelming number of photons that make up the cosmic microwave's background. It fundamentally set the energy budget and the composition of the early universe.
So the real importance of antimatter in the cosmic story isn't about causing an explosion, but about the mystery of its near disappearance. The puzzle lies in the asymmetry.
Precisely. The profound thing is that our universe isn't empty radiation. It has stuff in it matter. And that implies a tiny break in the fundamental symmetries of physics right at the beginning. Something allowed about one extra matter particle per billion pairs to survive the annihilation frenzy.
And figuring out how that happened, the mechanism of baryogenesis, whether through GUTs, EWBG, or the currently favored leptogenesis linked to neutrinos, is right at the cutting edge of physics.
It really is. It connects the grand scale of the cosmos to the nitty-gritty details of particle interactions, pushing us to find the deeper laws governing reality.
So here's a final thought for you to chew on. Our entire existence, every atom in you, every star you see, it's all just the leftover scrap from a near-perfect cancellation billions of years ago. Just one part in a billion survived. What does it really mean that we owe everything to such an incredibly tiny cosmic imbalance?